Application of linearly independent vectors. Proof that the diagonals of a parallelogram bisect each other. So let's make a parallelogram here. We know the opposite sides are parallel and they are equal. So that is what we know about a parallelogram. Now the question is that we need to say that the diagonals bisect each other. So that means if we have two diagonals, let's say this is one diagonal, right? And then we have the other diagonal, which is, let me join the other two. Okay, let's say this is this point. We need to prove that they bisect each other. That is to say that this side is equal to this side and that side is equal to that side. This is what we have to prove. Let us say that the parallelogram is ABCD, where A to D is a vector u, and if A to D is u, then B to C will also be vector u, correct? And let us assume that they don't bisect. In that case, they will be in some ratio, right? So let's say this value is V, then the other will be B times V, right? And let us say this side is, let us say, vector W. Then the other should be A times W. Scalar multiple, since they are indeed parallel, right? So they are along the same line. So that is how it should be. And let the midpoint for us be, let's say, E. Now in this case, let us solve for the triangle ADE. So what do we get in triangle ADB? Let's consider the triangle ADE. So vector u can be written as V minus W. Right? Now if you look at the other triangle, which is BCE, we get vector u is equal to, u will be BE plus EC. Now B is minus, let me give the directions also, be simpler. This is this direction. So vector u will be BV minus AW. Correct? Now since these two opposite sides are parallel and equal, equation 1 and 2 gives us that V minus W is equals to BV minus AW. Now we can bring all the terms to one side. So we get V minus, I'm writing this term first, BV, and here we have minus W, bringing that to get A plus AW equals to 0. Now we can take V common, so we get 1 minus B, V common. If I take minus W common here, then I get 1 minus A, I've taken W common, equals to 0. Now in this particular scalar equation, we know V and W are not parallel. Since V and W are not parallel, they are linearly independent, right? So these are linearly independent. Vectors, because V and W are not parallel, right? Secondly, since this is a scalar combination, this could be only true if the coefficients are 0, right? So if we, in general, we have, let us say, m times v plus n times w equals to 0. This equation is true only if m equals to n equals to 0, right? So, since they are linearly independent, the coefficients should be 0. And therefore, we get 1 minus b equals to 0 and 1 minus a equals to 0. That gives us b equals to 1 and a equals to 1. Now, if you see our diagram and our assumption, if a and b are 1, that means what? That means that AE is equals to EC. Do you see that? AE was V and EC was B times V. So that shows that AE is equals to EC and DE equals to EB, right? So that is how we can prove that the diagonals bisect. Right? So that is how we can apply the properties of linearly independent vectors and show that the diagonals of a parallelogram indeed bisect. Thank you.